Well, thanks for nice introduction. I'm Anthony, and today I'll be talking about quantum algorithms for thermal states. Unfortunately, Michael and Fernando can't be here today, but Andras is here, so if you want to chat with him, that's also very cool. Let's get started. So let's begin with this question. Let's ask ourselves, what are quantum computers good for? Okay, initially, this is a very theoretical question, so it started out being a very good complexity in algorithm research. But now this has actually become a very practical question because lots of industry and experimental groups are actually building a quantum device. And whenever we chat, they always ask us, theorists, so if we actually have a quantum computer, what are we going to do with it? So where is my application? Okay, what can you identify a very concrete case where quantum computer can have significant speed up over classical devices? Okay. So in fact, in this conference, I also chatted with people about this, and people seems to be pessimistic. And it seems that the reason is that there are just not that many examples that we know is very good. So factoring is one very cool examples. Seems very good for crypto, but not sure if it will extend beyond crypto. The other one is quantum simulation. Where it seems to be very popular, but somehow it has been very, very challenging to find. So very concrete cases where a speed up is like completely understood. Okay, maybe it's polynomial, maybe it's super polynomial, which is somehow very hard to get it very complete. And it seems that the problem is that quantum simulation is so promising that has so many applications, but then you also have to worry about lots of different systems. So fermionic, bosonic, is it long range, short range? What kind of physics you're looking for? But I would say that the bigger problem is probably that we don't have a really big quantum computer, but we have lots of very big and useful classical computers. So then I would say it's quite unfair for quantum algorithm designers that we don't have that much data to play with, while classical algorithms have all their heuristic and they're actually working. Right? But today, I really want to dive into this question and sort of give hopefully a fresh perspective on this by making this claim that perhaps low temperature physics is one such instance in quantum simulation that could have potentially big speed up. And so the supportive evidence we give is by providing an algorithm, a new algorithm for preparing thermal states. That's the title. Okay. And in fact, this problem actually has some super polynomial speed up in sort of restricted cases when you get to choose the Hamiltonian. Okay, so there was another talk it's very nice. You can also check it out. All right. So the whole starting point of our work is to look back to nature and think about what actually some empirical data we have about quantum algorithms. So in fact, there's one algorithm that seems to be working actually at very large scale, which is cooling. All right, so if you talk to experimental friends, if they're working on quantum experiments, most likely they have a big refrigerator and can go to very low temperature. And then they're able to use this to discover quantum phenomena. Right? So if you think about this from an algorithmic point of view, it's quite shocking that how good it is, that it's a very simple guiding principle, thermodynamics, just cool it down. But then at the same time, despite its simplicity, it's remarkably robust to errors and sort of perturbations. You don't really care about the particular details of a refrigerator except its temperature and cooling power. And most importantly, it seems to be working a lot. Most people are using refrigerators to do low temperature physics and quantum experiments. So I just want to use this example to borrow from this sort of shocking sort of what has been working at large scale and use this to inspire an algorithmic design. So the main question is, can we write down a succinct quantum algorithm that captures this powerful phenomena that we have been seeing for decades? Okay. And by designing such an algorithm, we get better control. Hopefully it will be more succinct, easier to analyze, and then perhaps allows us to prove things about how this works. Okay. Right, so that's today's task. We're going to prepare quantum thermal states. So given a quantum Hamiltonian and a quantum computer, our goal is to prepare a thermal state in our quantum memory. Okay, so this is also called a Gibbs state, depends on your background. It's a quantum state that could be very entangled. Its density operator look like this. It's so defined in an energy basis as certain mixture where the high energy states are penalized by the exponential factor. In particular, if you go to very low temperature or very high beta, okay, this becomes the ground state. Okay. Right. So our approach to this problem can be understood from two very different perspectives. So on the right-hand side is cooling, which is sort of the motivation I was giving you. So what we're doing is just to capture this physics into very concrete mathematical algorithms. On the left-hand side, this actually can be understood from a CS point, where can regard this thermal state preparation sort of as a quantization of this classical Gibbs sampling. So historically, the classical simulation people actually at the same position as of today. They want to simulate classical thermal state of Ising models, and this is sort of what they found. A classical MCMC algorithm. And MCMC algorithm has ever since found lots of other applications, just because it's so simple to use and at the same time very robust. Okay? So that's how we can understand today's work. We call it quantum MCMC algorithms. That it's a quantization of these classical Gibbs sampling or classical MCMC methods, or an attempt to capture cooling. Right, so let's begin with classical MCMC, because a lot of the framework is really sort of very straightforward, generalized to the quantum case. So classical Markov chain Monte Carlo is the idea to construct an efficiently implementable Markov chain. So it's a matrix where you want two nice properties. So first, it's the thermal state is stationary. So this pi is supposed to be a classical thermal distribution. And then you also hope that when you run this algorithm for a long time, it converges to the thermal state. Okay. And then from this, you can actually just read out the cost of almost any Monte Carlo algorithms. It's just like the cost of each Markov chain updates, and then how long you're going to run it for. So just multiply these two, and you get the cost. And of course, if you want to extract physical observables, you might have to do a lot of shots. So there's like this 1/epsilon scaling that's sort of hidden away from here. Okay. Right, so just give you a very quick example. This is a Metropolis Hastings algorithm. It's invented 70 years ago, but still being used today because it's so simple and so robust. The inputs, so as a user, you just need to choose some classical Hamiltonian, such as Ising model. Right, so say today we want to simulate physics of magnets. And then all you need to decide is what temperature you want. Is it high temperature or low temperature? And then what set of jumps you're going to allow. Right, in particular, let's just take them to be single spin flips. So on each, on this 2D grid, you're going to flip individual spins. Okay. And then that's the input. For the output, you hope that your algorithm converges to the stationary state, which is the thermal state, and you can see the physics of this state. And then that just manually go through this animation. Okay, so you started out with an Ising model at a certain temperature and some magnetic field. And what's going to happen is that the spin is going to try to align with the magnetic field. So the energy and then the magnetization also start changing. It looks like this. And then eventually it sort of stabilizes. And now the algorithms just converge. Okay, so from here you can sort of just guess that the mixing time is roughly 2, where all the physical observables just converge to a stationary value. Okay? But of course, this is not the only thing you can see. In some cases, maybe it takes a long time to converge. Maybe sort of drastically change its behavior. Then this is sort of a very nice observation would be for the physical properties of this model. Right, so if you see something weird, that means that you're seeing phase transitions or some interesting physics. Okay, so to recap, people just use this algorithm to study magnets and really have uses to just basically understand magnets very, very well, like phase transitions and all its properties. Okay, so this is sort of the starting point to go to the quantum one. right? So classically, you have all this laundry list of the thing I just told you, right? And there's an efficient classical algorithm. And then what we're doing today is to quantize the whole thing, right? So the configuration can now be quantum because you have quantum memory. The thermal state is a quantum thermal state. It's non-commuting, so no, it could be hard to store classically. Your Hamiltonian in particular could be also non-commuting, or its eigenstate should be very entangled. Your jumps can be all sorts of unitaries you can think about. In particular, includes Pauli XYZs. And the algorithm we present today is the sort of suitable generalization that does this. Right, so that's our main topic. So here's one thing that you might want to try. How to quantize the classical Markov chains. So you might just say, well, why don't we just do random walk on energy basis, right? So if this is the energy, the horizontal is energy, and then each site is like some energy eigenstate. So suppose you start with an energy eigenstate I, psi I, and you apply a jump. So say it's like a Pauli flip. And then it's going to change the energy, so it's going to sort of have transition to other energy eigenstates. And you're going to try to enforce this rule that if the energy decreases, you're going to say accept. If the energy increases, you're going to reject with some carefully chosen probability. Okay. So in some sense, this is just trying to do metropolis hasting on the energy basis. Right? So pictorially, we have these blue transition rates, and then you sort of sometimes want to go back if the energy increases. And then in this case, you would sort of favor the lower energy transitions, and then hopefully this will converge to a sort of like a low temperature thermal state. However, this should feel a bit uncomfortable for you if you sort of have a feeling of quantum mechanics. So first, you have to make a decision depending on the energy change. So it almost smells like metrology, right? But then in quantum mechanics, metrology is very expensive. And the second, if you're in the second case, you want to reject, it's not entirely clear how you do it because you cannot have copies of quantum states. You also don't actually know what these energy eigenstates are. Right? So how do you reject without already knowing what they are? So you see, in order to design a sort of a quantum version of Markov chain Monte Carlo algorithm, there are sort of these very fundamental problems sort of in conflicts with the quantum nature of this. Okay? So in fact, these problems sort of have haunted all these existing constructions. So there's really roughly two kind of families. So one of them is sort of just make the energy measurements perfect. So you sort of just assume that you can measure the energy perfectly. So this is not physical, right? Because you can't really implement it so efficiently. But then it makes things nicer and sort of gives us a lot of nice intuition. But then there are another family of approaches that try to sit down and then make energy measurements realistic. It gives algorithm that you can potentially implement. But then you sort of open up a whole can of worms, right? Because of this energy uncertainty, you break detail balance. The whole map becomes sort of monstrous. It's really hard to write down. And the algorithmic costs also just explode or just unproven. Okay, it's just so complicated to analyze. And in particular, there are sort of two families approach. One is from CS, so like try to emulate metropolis hasting. The other one sort of just go back to what physics is doing. And in both cases becomes very messy. So I think it would be fair to say that as of today, we don't really have a go-to quantum MCMC algorithm if someone wants to analyze this. Maybe you want to do some numerics, you want to do some resource estimate, maybe you want to do some analysis. It's not very clear which one you would pick because they're all just so complicated. Okay? And the main contribution of our work is to sort of clean all this up and give we think is more or less optimal construction that has the very nice properties, that it has exact detail balance. The energy measurement is still sort of realistic and implementable. It has very simple analytic form. And also have a very, very low algorithmic cost that is optimal. So we think that this would at least be a starting point to further understand these algorithms, as a rigorous formulation of cooling, and it could be a good start to start doing numerics and analysis of these algorithms. Okay. So this is what our main algorithm is. It takes the form of a continuous time quantum Markov chain, which is often called a Lindbladian, or master equation, or Liouvillean. It just looks like this. Don't ask me. It's in your textbooks. In particular, it has this coherent term and some distributive term. And all of this just to ensure that it sort of makes sense as a CPTV generator. Okay. Well, of course, the real question is how do you choose these B and Ls so that it's nice, right? So then the problem is how do we design this algorithm so that it satisfies quantum detailed balance? And that implies that, like the classical case, it will fix the thermal state. Right, so let's talk a bit about detailed balance. So classically, detailed balance is sort of a rule or like some symmetry between pairs of transition, between pairs of configuration. So I have these red and blue arrows. It's sort of like the heating transition, which increases energy, is related by the cooling by this particular number. Okay. And that's detailed balance. It tells you that the Markov chain fixed the thermal state. Well, quantumly, this becomes slightly different, but not entirely too shocking, is that because quantum inputs has both Bros and Kets, so this energy eigenstates can be Bros and Kets, so the whole thing becomes two-dimensional. And then you can write down a corresponding sort of detailed balance rule that you want that would ensure thermal stationarity. Right, so mathematically, this looks clean and simple. However, for algorithms, this is actually quite sort of questionable because you don't actually have access to these energy eigenstates. Right? Metrology is very expensive. You don't know what these energy eigenstates are. It's hard to write them down. So how do you implement these while you only have fuzzy energy measurements, right? But you sort of want this detailed balance to hold exactly. So how do you do that? And that's precisely our main contribution, is sort of to find very efficient algorithm that does this in the right way. And here's our theorem. We construct the first exactly detailed balanced, but yet efficiently implementable quantum thermal state preparation algorithm. So pick any Hamiltonian you want, any temperature you want, and any set of jumps. We give a general recipe of constructing a Lindbladian, so a continuous time quantum Markov chain, such that with the following two nice property holds. So first, the thermal state is stationary. This came from detailed balance. And second, the cost per jump, per unit time that you implement this algorithm, so exponential L for constant time, has a remarkably cheap cost. It costs very few ancillas and only beta black box Hamiltonian simulation time. Right, to understand this, this is a general purpose algorithm. We only need black box access to Hamiltonian simulation. And then you can refer to literature of what are the existing method of doing this. That's all black boxed. But then you still have some tunability of this algorithm, just like classical Monte Carlo. There's still some, you can still choose these jumps. Sometimes you might need better jumps to make some problem. And remarkably, you get exact detail balance in a quantum world while using a very short sort of time measure, like a very short Hamiltonian simulation time. Right, so this corresponds to a very, very sort of finite energy resolution. That's 1 over beta. And somehow this is enough to give exact detail balance. Right, so in the end, suppose you want to convert the cost of an actual Gibbs sample. This is what it will be. It would just be the cost per step and times the mixing time. Right, so this mixing time could depend on problem. For easier problem, it might mix very quickly. For hard problem, it might mix very slowly. Right, but that's just a feature of general, even classical MCMC algorithm has this feature. right? So even nicer, our construction have a, sort of like some bonus property, is that if you apply our algorithm for lattice Hamiltonians, it has very nice property that the Lambdadians is actually a sum of quasi-local terms. So you can think of this as like a local distributive map that all of them sort of fixes the thermal state globally. Okay. So what seems to be very cool is that you get global detail bands, so it fixes the global gift state, while you only use this sort of local information about the Hamiltonian. So each of these LA can be constructed locally. And then the size of these localities is roughly order beta. It's just coming from the Hamiltonian simulation time. No, it's really coming from light cone argument. Right? And in particular, for community Hamiltonians, since the light cone is constant, so this locality further reduces this recover known results. But if you're interested in ground states, this is also possible. Then this would correspond to setting this beta to be corresponding sort of the inverse gap. Namely, we got a quasi-local algorithm for thermal state and ground state. Okay. So another additional nice property is that our formalism is entirely compatible with quantum walks in a sense that it lives to apparent Hamiltonian if you double your Hilbert space. So this shouldn't look too surprising, but it's just very nice. I just want to write it. So then what happens is that you get actually an adiabatic algorithm for the purified thermal state, which is known to some people as the thermal field double state. What you need to do is just to double your system size, and there's a sort of prescription of lifting our map. Okay, so you get this very nice dictionary that a fixed point becomes a zero eigenstate, and then this Markovian dynamics in time becomes like an adiabatic evolution in the inverse temperature. Okay. So in the remaining of time, let me just mention how we do this. This is very highly inspired by some physics sort of exists in the physics literature, but also requires some tuning and to make this actually work. Okay. So the secret sauce behind our recipe is the operator Fourier transform. This looks like some integral. There's some Fourier weights, exponential I omega t, some time, so some weight that's f of t, and then some integral over these Heisenberg dynamics. Okay. From here, you can see that it's localized in time once you choose this f to be sort of have a finite time window, or in particular like a Gaussian decay. And this is where the beta, so if the beta locality comes from, if the Hamiltonian is local. It's a light cone. But at the same time, it's also very nice in the frequency domain because it's a Fourier transform. So if you go through a Fourier transform, you actually directly diagnoses the energy difference before and after the jump. But pictorially, what's going to happen is that if you apply this operator Fourier transform to an energy eigenstate, it's going to map you to sort of like a blob of states that has energy roughly increased by omega. But then it has some uncertainty, so this blob of like Gaussian packet. And the right-hand side is like a matrix representation of this in an energy basis. So it's going to look like some off-diagonal band. So with this, you can actually present our the form of our Lambdadian. Of course, to actually simulate this is another thing, but we can also do that. But here's what it looks like. Okay. So it features this operator Fourier transform as the main object. And the point is that these operator Fourier transform are very smooth and sort of localized quantity in time. We only use this like finite time to implement them, so they correspond to a finite energy uncertainty. Nevertheless, you can get detail balance exactly. And the point is that detail balance is actually a very smooth property, and then you're just manipulating some smooth object. So it's sort of like QSVT at a very high level. And then once you put these operators there, you actually also want to sort of bias them, because then you want to penalize the heating transitions. Right? So you also want this sort of Boltzmann rule to apply here. And all you need to do is just put some number there to weight different energy transitions, and then integrate over all possible energy change. And here I just want to say that somehow in this continuous time picture, detailed balance is a lot easier to do. And you don't have to worry about rejection. Just somehow when you go to continuous time, rejection is sort of automatically avoided. So it's a little hard to explain, but just somehow it's very nice. And then there's this weird term, this coherent term I never get to tell you about. It has sort of some physical correspondence, meaning, but I would just say that mathematically this appears as a unique and necessary solution to detailed balance. It just come out of this, like when we solve the equations. Okay, so that's more or less what I want to tell you. I just want to say that, so now we just found this algorithm. We're all very excited. You can check out these short and long paper. But it seems that this could potentially open up a new playground. And one of them, obviously, is the proof of mixing time. You know, in QIP, you see some talks that already did this for commuting Hamiltonians. But then we sort of give like the suitable non-commuting analog, so it just allows you to prove this. So now this is possible that you might be able to prove it, you know, in a few years. But then, since classical MCMC algorithm has been applied to places beyond physics, we also expect this quantum thermal state preparation or quantum Gibbs sampling algorithm could potentially have other uses. And potentially this could lead to new speedups. And of course, you know, mixing time is a very daunting object, but we have just made some initial progress on this, in particular in the context of local minimum. So I want to tie it back to the original motivational question, is that, you know, whether quantum computers will be useful for anything. Of course, we hope this algorithm will be one of those algorithms. But to justify that, certainly need further simplification and then perhaps even numerical studies of them, so as to lead to an end-to-end resource estimate. And also, this algorithm, since due to its sort of physical origin, it seems to touch upon a lot of physical ideas that already existed, you know, like area law, you know, phase transition, quantum memories, decay of correlation. So you already see like some talks already sort of directly related to this. So I think it's really like a really nice playground, very exciting. So yeah, so welcome all you to join this area, and let's work together. Thank you.
Okay, we have time for one or two questions. If you have a question,
Thank you. So I guess I have a question about the mixing time point. So are there any instances, sort of non-trivial ones maybe, where you can prove that the mixing time is actually efficient for use?
So I think so for lattice system, this is sort of only done in a commuting case, but it's still yet to be done. But I think the obstacle to that is just that this map has not been defined. Like it's not, I don't think there's like fundamental obstacle to that. And then in other work about local minimum, we do set up like a sort of a classically non-trivial instance. So it's like some circuit to Hamiltonian mapping where we prove that it's mixing.
Okay.
So I think it's open because the map has not been defined.
Okay, thank you.
one more question.
Thank you. So in principle, what you wrote down is the physical evolution of the system if it couples to the environment. And there is a technique to simulate that on a classical computer, which is to unravel it into stochastic master equations. And that saves you a lot of space, actually, at least classically. Have you tried that on a quantum computer?
In some sense, you can. I haven't told you about how we simulate this, but in some sense, you can interpret that as our simulation algorithm as also unraveling that, but that you can store quantum states. So classically, you still have to sort of write down the whole quantum state description, but now you sort of use your quantum memory to store that. So in some sense, it's very close to what classic, the unraveling is doing. Oh, I haven't tried it on the actual quantum computer, but but yeah. But I would just say that the algorithm we implement can be interpreted as unraveling if you keep all of the information about your path, because like an algorithm has to trace out things, and then if you keep all of those data, you can sort of track the trajectories.
Okay, I think if there are more questions, we should take them, offline or during the lunch break. And let's thank Anthony again.